Welcome to our lecture on the FICK method, part 2, where we examine how to use standard worksheets to perform real, actual FICK calculations. This is John Boland. We saw in our previous lecture, this is my standard worksheet, similar to what others use, although mine is simplified into 4 separate steps. You remember we collect patient details. The important ones are height, weight, age, and sex. Then we calculate our lung gas values to work out our oxygen consumption. A third step is to do a blood gas analysis, and using these 2 steps, we work out our calculation of cardiac output by the direct FICK method. Along the way, we'll work out the indirect at the same time. This is the first morphometric chart we use for the indirect FICK. It's a calculation of surface area based on the patient's height and weight. It's a simple enough process. Morphometric charts consist of 2 vertical bars and a third bar. Knowing the value of any 2 points on these vertical bars gives us a value in the third simply by drawing a line across the 3 that intersects the 2 known values. In this case, height and weight, to obtain surface area. There is also an equation called the Dubois equation, on which many of these are based, and there are more than one equation, but Dubois is the most popular equation, and it's available readily as an app you can download onto your phone, or it appears number 1 on most calculators to convert height and weight into surface area. The other 2 morphometric charts used in the calculation of indirect FICK cardiac output are estimates of basal metabolic rate and heat production. We normally always know the patient's age, and we assume a basal metabolic rate of 0 because the patient is at rest with no physical activity. And that is the basis for our resting heat production value. Note also the age column is divided into 2 sections, one for males and one for females. Note also that the age column is divided into 2 sections, one for males and one for females. And after years of use, you remember that females aged 65 and over have a basal metabolic rate of 33, and males aged 65 and over have a basal metabolic rate of 35. They're useful values to remember because so many of our patients are elderly. Knowing our heat production, say we take it to be 35, and we know our surface area, take it to be any value, whatever it is, you draw an intersecting line between those 2 points to derive your oxygen consumption. And the process, it's as simple as that once again. You do it a few times, you'll always remember it. So, doing a real example from the patient that we did our example calculations in the previous lecture. A reminder, the height was 168 centimeters, weight 54 kilograms, age 54, and sex female. From this morphometric chart, if we line up height and weight, height 168 up there, and weight 54, we get a line of intersection at 1.6. And I was able to match that line almost perfectly. So the body surface area is 1.6. You can do it very quickly or punch those numbers into your Dubois equation in your app or PC or calculator and you'll get the same answer. The other 2 morphometric charts are used in conjunction, as you saw. We want to know the heat production to get the oxygen consumption. So the patient was 54. Basal metabolic rate was 0, and the heat production was 35. In this case, it was impossible for me to align the red bar perfectly over the zero. It shifted either above or below, but on paper I could do it quite easily, and believe me, the heat production was perfectly 35. So we line up the 35 mark for heat production on this chart, line up a line of intersection with a surface area of 1.6 and extend it to the oxygen consumption, which here lines up almost perfectly at 200. Remember, your apps can do the calculations directly using an equation called the Metienen-Lafarge equation. That is a lot more complicated and takes a little more punching in of data, but it will give you pretty much the same answer. It's your preference what you do, although your generation, I'm sure, really touches pen and paper. So let's have an example of the direct FICK method using a different patient. I've shown you how to do the indirect measurements. Let's now do a direct measurement for a separate patient. Height 157 centimeters, weight 69 kilos, age 88, sex female, with a body surface area of 1.7. This patient presented to the cath lab for right heart catheter investigation of a heart murmur. This simple chart gives us a body surface area. Knowing our height and weight, I was able to align the line almost perfectly once again to get a body surface area of 1.7. Simple enough. The other two morphometric charts, the lady was 65 years and over, and I've said previously that it's 33. Again, it's not a perfect alignment, but believe me, on paper, that's what it comes to. And the O2 consumption, surface area 1.7, heat production, and it's not perfect, but that value is just below 200. And on paper, the value for oxygen consumption was 195. That's just the difficulty with the limitations of electronic drawing, but it's not going to affect what we're doing. I'm just demonstrating how the system works and how we derive our values for the indirect FICK. So we go to our worksheet. Remember, we've entered our patient details here. We then have to do our lung gas analysis. And that involves collecting a Douglas bag over a period of rest, say 2 or 3 minutes, collecting the exhale gases. We then convert to standard temperature and pressure. Remember, that Douglas bag is contaminated with water vapor. Water vapor exerts its own pressure, as does any gas, any separate group of gases in a contained environment, one of your gas laws. We have charts, separate charts, that can tell us the impact that water vapor pressure has on that collection of wet gases. And once we know it, we subtract it from the millimeters mercury atmospheric pressure of the day and use that value and the temperature of the day from another chart to calculate a conversion factor. And that conversion factor multiplied by the liters per minute gives us our corrected liters per minute exhaled at standard temperature and pressure. Sounds involved, and it is, but we'll work through it and it should be clear to you. Then we have to work out our percent composition of the exhaled gases, meaning we need to measure components oxygen and carbon dioxide. And from that, the difference will be percent nitrogen, which should not vary very much from our known standard values. And we apply a formula to give us our O2% difference, and that value that we get there multiplied by our volume exhaled at STP over 1 minute will give us our O2 consumption. In words, it all sounds very complicated. Once you have a standard format to follow, it's much easier to follow, believe me. Then we analyze our blood gases, totally separate independent procedure. where we calculate our saturations for arterial and venous samples, convert them to oxygen content, and then enter the values into the calculation for the FICK equation. Remember, the denominator is the arteriovenous O2 difference. So we need to know the value for the arterial and the venous oxygen content. And the difference divided into the oxygen consumption gives us the cardiac output. Again, in words, it's tedious, and it is tedious on paper as well, but it's easier to understand seeing the figures, which is what we're about to do now. Starting with a blood worksheet. Remember, this can be the first or the second step. It doesn't matter which one you do first. Depends on how many staff you have, what resources you have, and the circumstances of the day. In this case, we collected blood at rest, patient lying down, from the pulmonary artery and the left ventricle. Hemoglobin was measured at 13. Multiplying hemoglobin by 1.36 gives us the theoretical maximum oxygen carrying capacity. We get our saturations by directly measuring in a hemoximeter or some kind of blood gas analyzer. We do them in duplicate, depending on the machine, and we average those to get a representative value, which is very close to either of those two, in this case 66.2% for the pulmonary artery and 93.1% for the left ventricle. And we convert that to oxygen content. Now, I've shown you how to convert saturations to oxygen content. Think for a second, do you remember how to do it? Look at these figures, and which figures do you use? You either know or you don't, I'm afraid. You take this value, oxygen carrying capacity, 17.7, and multiply it by the oxygen saturation as a decimal, 0.662. So 17.7 times 0.662 equals 11.7. That's your venous oxygen content. 17.7 times 0.931 equals 16.5. That's your arterial oxygen content. The difference between these two is your arteriovenous oxygen content difference. That is simple enough if you remember the mathematical steps. The same patient, step 2 in the calculations. We now do the lung worksheet. Now remember, VO2 calculation is itself a two-step process. You can either do the calculations manually or use the Metin-Lafarge equation app that you can download, and you put a lot more information into that, but you get essentially the same answer. So let's start. You collect your Douglas bag from the patient, ensuring there are no leaks as much as you can, reassuring the patient that he'll be able to breathe. Some patients have never used a snorkel before, particularly the elderly. Some of them have weak jaws and don't have the strength to keep a firm bite and a tight seal with the lips around the edge of the mouthpiece. And you have to clamp the nose off with a little nose clip. And they can be uncomfortable breathing through the mouth because it dries the throat. And when you do it for 3 minutes, it's an uncomfortable feeling. So we use the remaining value from the last patient on the volume counter, in this case 985.83, and after emptying a bag by squeezing every last volume of gas out, we get a new reading of 1011.43. The difference between the two is 25.6. Dividing that by the 3 minutes of collection, we get a value of 8.5 liters exhaled, but that's wet gas. We have to eliminate the influence of water vapor on that gas volume. We measure the temperature in the room and the atmospheric pressure on the day, and we go to our morphometric charts. And I'll tell you now that at 22 degrees centigrade, water vapor exerts a pressure of 20 millimeters mercury on a sealed environment or a contained environment in a wet environment. Once we know that value, we subtract that from the known atmospheric pressure of the day to get a new value, corrected for standard temperature and pressure. And we look at another separate chart to get the STP correction factor for air at 22 degrees centigrade and 74 degrees mercury in the dry state, excluding the influence of water vapor. Let's go through the process and then we'll be able to do this calculation for O2 consumption. This is our first chart. The correction tables here are relatively straightforward. Here we have temperature ranging from 0 to around 35, and here we have the influence of water vapor, a figure up to 2 decimal points. We normally round it off to the decimal point. So at 22 degrees, we get a correction factor of 22. That's what it is. At 22 degrees, this little chart here tells me water accounts for 20 millimeters mercury in that bag. Then in one of these big tables, we subtract 20 millimeters from 764 millimeters, the atmospheric pressure of the day, to get 744. So here, wherever it is, we don't need to bother to find it. It's enough to know that the wet and dry atmospheric pressures are both shown under the value for the atmospheric pressure of the day. So you find your 744, you find the column that's dry atmospheric pressure, and you look up this 4-digit value. And that's all we need to obtain from these charts. Again, it's tedious and initially a complicated, even confusing step. But once you do these, at least a few hundred times, it becomes second nature to you. That said, I doubt very much that you will ever have to do these. I'm not aware of too many hospitals these days who are doing the FICK. It's expensive and tedious and time-consuming, ties up lab time, and it's technically difficult, requiring the right resources and the right personnel. And many labs no longer have those facilities. Back to our worksheet then. That value that we obtained would have been 0.9211. We multiply 9.54 by that fraction to obtain the new value, so that 9.54 wet volume now becomes 8.8 dry liters of air exhaled per minute. A long step, but essential. A second step in the lung gas analysis is to directly measure a little sample of that bag to get oxygen percent composition and carbon dioxide composition. And the difference between 100 and these two values is 79.1, which is close enough for our purposes to the expected value of nitrogen, which we take to be close enough to 80%. And this is also an indicator of the accuracy of our measuring instruments. Even though they're calibrated every day, they can drift slightly up and down, and that introduces a slight error margin. The next step is to use these values to calculate the oxygen percent difference. What does this mean? Well, this tells us what percentage of oxygen the patient has breathed in from air after breathing out. It tells us the amount of oxygen the lungs have consumed or extracted from normal oxygen in air. And that, multiplied by the volume exhaled per minute, gives us our oxygen consumption. It sort of makes intuitive sense. If you're extracting a certain amount, 1.4%, with every liter, then the more liters you consume, or the more liters you breathe out, then that will give you your total oxygen consumption over that period of time. Once we do that, we get a value of 120 once we correct for decimal points. Now, notice this one. The calculated value is lower than the assumed or expected value. Our assumed or expected value from the morphometric charts works out at 180 mils per minute. And why is this? Well, you wonder why the supposedly more accurate method is inaccurate. And that is because not every patient, as I said, is able to accommodate the apparatus. And despite our best efforts, they can either have a leak or somehow just not breathe at the usual rate, and that can lower that value. Whatever the reason, if this value is lower than the expected is the lowest value it can theoretically be. So any lower value is theoretically impossible. So we just discard it and use the assumed or expected value. That is why in my calculations, my worksheets, I always do both. And in this case, if you use an VO2 of 180 divided by your arteriovenous oxygen content difference, which comes from the difference between your arterial and venous oxygen content, 14.9 minus 10.4 equals 4.5. 180 divided by 4.5 gives us a cardiac output of 4, which is realistic for a lady of her age and physical condition. We routinely also calculate cardiac index, and that's obtained by dividing cardiac output by the body surface area. And to be satisfactory, it's considered to be around 2. Less than 2, there's a little grounds for concern. Anything above 2 is excellent. That's enough for this lecture. We've stuck reasonably well on time. There's a lot of other considerations to discuss, but some of them need to be done in a tutorial type of session, and I'm sure by now you must be full of questions. Please read whatever references I've given you and read on your own any topics online or books of your own that you have, and that will become clearer. There are different ways of explaining the same things. I can only choose the one that I think is best for you to understand and the easiest to explain in a short presentation like this. But don't be too concerned. Everything is difficult at first until you know it. With that, I'll close this lecture.